Welcome back everyone to MAE170. This is lecture 16 in week number 10, last lecture. So to conclude the course, I want to go over something that we haven't seen so far, which is uh, how a feedback system reacts when it's subjected to some changes that are not foreseen. For instance, how does a feedback control system react if there are some external disturbances? How does a system react when there's some measurement noise? And finally, how does a system react when some parameters inside the plant might change over time? So if the transfer function describing the plant changes, how does that compromise the performance of a feedback system? So you're going to find um, this. So this is called error signal analysis and system sensitivity in chapter 4 of the textbook. And this is called error signal analysis because we're going to see how the tracking error of the feedback system, the tracking error is what we've been calling simply error so far. That is the input minus the output. How this error is affected by, again, external disturbances, measurement noises, and changing in the plant transfer function. So now we're gonna take a look at the block diagram of our feedback system, which looks almost identical to what we've seen, with the exceptions that we have two extra sum injunctions. So let's start by considering the usual input, R of S, and to the input, we subtract the measured output, and the signal that comes out of this junction, we're going to call it EA, and we're going to see later that this is not actually equal to the tracking error. So the tracking error, as I said, it's just the input minus the output. This is not going to be the same because we have this extra two sum injunction. And in the first sum injunction, after the usual one, we have as the input the external disturbances, which are added to the control signal. So the disturbances are modeled so that they enter the system after the control, because if they were entering before that, the controller would take care of that, but the disturbances are not taken care of. So those are, if you can think about them as variations in the inputs, which are not accounted for by the controller. Then we're gonna name the signal that comes out of the second sum injunction as Q of S. And finally, we have our usual output, Y of S. And when we measure the output through the sensor, there's usually some noise associated with the measurement. And so the noise will take part into this block diagram, and it's going to be added to the output. So what we think we're measuring is just Y of S, but instead we're measuring the actual output plus some noise. So the signal EA is what we think is the error, but it's not the real error. And that is R minus X of S. And X of S is Y plus the noise. So that's why the signal EA is not equal to the tracking error if we have some measurement noise. So once again, in this lecture, we're considering a broader perspective with the introduction of the disturbances and the noises. All right, so TD, as we said, represents the disturbances, and N of S, the measurement noises. Okay, so as I said earlier, we want to see the effect on the tracking error due to, well, the input, the disturbances, and the noises. So we have to find out an expression for the tracking error. And once again, we're looking at R of S minus Y of S. So let's start by simplifying this block diagram, and let's look at the output first. So the output is given by G of S. Remember, we start from the output and we go backwards until we meet a signal after a sum injunction. So that is G of S times Q of S. Now, what is Q of S? That is TD plus GC, the controller, times EA. And what is EA? Well, we wrote it earlier, but let's rewrite it. That is the difference between the formal input, if you wish. Again, here you can think about TDS, R of S, and N of S as all inputs. However, R of S is the input as the desired output in the usual convention for feedback control systems. So EA of S is equal to R minus X. And finally, X is given by Y plus N. Okay, so if we substitute X in here, E of A in here, and Q over here, we can rewrite the expression for the output, and that is given by G times TD plus GC that multiplies R minus N plus Y. Okay, let's do some more calculations. Let's expand. So we have GS G times TD plus GC G R, and then minus GC G N, and lastly G minus GC G and Y. So we're going to take this term and bring it to the left-hand side of the equation. And so we can explicit Y as G of S over 1 plus GC G times R. So this kind of looks familiar, doesn't it? But we have two more contributions. So those depend on sorry, we have GC here. There you go. We have two extra contributions that depend on the fact that we have disturbances and noises. So the transfer function between the disturbance and the output is G over 1 plus GCG. And then finally, we have minus GCG over 1 plus GCG that multiplies the measurement noises. So you can see if we didn't have disturbances nor noises, then we would end up with the usual relationship between the output and the input that depends on the transfer function of the plant, that is G, and of the controller GC. However, if we are considering, as we should, disturbances and measurement noises, then we have two extra contributions, one with the plus sign and one with the minus sign, corresponding respectively to the disturbances and to the presence of the measurement noises. However, as I said, we are interested in seeing the contribution to the tracking error, so we have to write down the tracking error function. So we simply have to take R and subtract what we just, the expression that we've just found for the output, that is R minus Y. So if we do that, then E of S, that is the tracking error, can be written as 1 over 1 plus GCG times R of S. And once again, this looks very familiar. This is the usual expression for the error function that we've seen so far. However, once again, we have the presence of disturbances and noises, which will contribute to the tracking error. So we have the disturbances that contribute as minus G of S over 1 plus GC times G. And for the measurement noises, there we go. So we can rewrite this expression by using a more compact form, remembering that we've used the expression L of S for the product of GC times G. So that is our loop transfer function. And so we can write the error, the tracking error, as 1 over 1 plus L times R minus G of S over 1 plus L times TD. And finally, plus L over 1 plus L times N. Okay, so we already know everything when it comes to the error function and when we only have the input R of S. Now let's take a look at the contribution due to the disturbance, which is also known as the disturbance rejection. In other words, let's see how well the feedback system can reject external disturbances. And if we want to focus exclusively on the performance of the system due to the disturbances, let's assume that we have 0 input and 0 measurement noise. So if we have only the disturbances, how does the tracking error look like? So for R of S and N of S equal 0, then the tracking error, and then we're going to call it TD, because that's just the contribution of the disturbances due to the disturbances, is equal simply to G of S minus G of S, over 1 plus L of S times TD. And so magnitude-wise, if we just take a look at the magnitude of this transfer function, that is given by the magnitude of G of S over 1 plus L of S times the magnitude of the disturbances. So qualitatively speaking, if we want the error due to the disturbances to go down, we want the magnitude of our loop transfer function to be high because it's at the denominator. So if L of S is in magnitude is high, then E of S is going to be small. So a high magnitude for the loop transfer function will result into a small tracking error due to disturbances. So we're gonna reject external disturbances much better if the magnitude of our loop transfer function is big. Let's see what happens when we want to take a look at the error function solely due to the measurement noise contribution. And this is also known as the measurement noise attenuation. So in this case, we're going to assume that the input and the disturbance is 0. And let's take a look at just the contribution due to the measurement noise. So we have that our tracking error when R and TD are equal to 0 is simply L over 1 plus L times N. Or if we take L of S, that multiplies 1 over 1 plus 1 over L of S times N. So once again, if we just consider the magnitude of the error, so the magnitude of the transfer function, that is given by the magnitude of L times the magnitude of 1 over 1 plus 1 over L times the magnitude of our measurement noises. So here you see if we want to reduce, so to attenuate the noises, in other words, to reduce the tracking error contribution due to the measurement noises, we want the magnitude of our loop transfer function to be low. Because if L of S is low, then this the overall contribution, the overall transfer function here decreases. And so that attenuates better. So a feedback control system that has a low magnitude of the loop transfer function attenuates better measurement noises. However, we see that we have two contrasting requirements, because if we want to reject disturbances, we want the magnitude of L of S to be as high as possible. But if we want to attenuate the measurement noise, we want L of S that is small as possible. So it seems that we cannot have both. However, we are kind of lucky because disturbances and measurement noises are signals that are characterized with different sets of frequencies. The disturbances are usually signals that are associated with low frequencies. Whereas N, so the measurement noises, are associated with high frequencies. So maybe the disturbance, it doesn't have to be precisely one sinusoidal wave, but a combination of them. But it has a low frequency, whereas the measurement noise might have high frequency. So we can actually design our loop transfer function so that it is high at low frequencies and low at high frequencies. For instance, if we have here, this is the Bode plot for L of S. Of course, this is the magnitude of it. So it is 20 logarithm of the magnitude of L of S. As we said, we want to have high magnitude for low frequencies. So that's what happens over here. And we want a small magnitude at high frequencies. So in this case, it works. So if we have a control system whose loop transfer function has a Bode plot magnitude that kind of looks like this, then it is ideal for rejecting disturbances and for attenuating measurement noises. Okay, so now let's take a look at the third thing that I was talking about in the very beginning, and that is how a control system performs if there are some variations in the plant parameter. So that is the so-called sensitivity. So now I want you to think about the following scenario. Let's say you have a process you want to control, and you can think about the usual mass with the spring and the damper. And the mass oscillates, and it's, we know the input, we've modeled everything very well. So we've designed a control, and we're very satisfied. However, let's say that the stiffness of the spring changes over time. And so obviously the controller, which has been designed for the nominal value of the spring stiffness, is not going to work as well. And the output, so the position of the mass, is not going to be as what we really wanted. So how well can a feedback system cope with changes in the system parameter? So if the system parameter change can be modeled as simply a variation in the process transfer function. So let's say that after a little bit of time, we go from G of S, which is what we started from, to a slightly different transfer function for the plant, GS plus a small variation, delta GS. So once again, let's take a look at the effects of such change on the tracking error E of S. And here, we're going to assume that the disturbances and the measurement noises are absent. So we solely want to see how the system reacts in terms of the tracking error due to changes in the plant's transfer function. So we're going to have that here. Let me just, the change in the tracking error. So we're going to have the usual tracking error plus an extra contribution. So our new tracking error is E of S plus delta E of S. And that is equal to 1 over 1 plus GC. And here we would have G, but now we have the new plant. So that is G plus delta G times R. Now compare this to the tracking error function without the modification in plant transfer function. That was 1 over 1 plus GC times G times R. So if we substitute the expression for E in the first equation, and we explicit delta E of S, so the increment in the tracking error due to the change in the plant's transfer function, we're going to find that that is equal to 1 over 1 plus G plus delta G. I'm going to drop the argument S for sake of time, times R minus 1 over 1 plus GGC times R. All right, so now we have 1 plus G plus delta G multiplies GC, and multiply 1 plus GGC. So at the numerator, we have 1 plus GGC minus 1 minus G plus delta G, GC. So we have that 1 goes away with minus 1, and then GGC goes away with G because that is multiplied to GC. So we are left with minus GC delta G over the same denominator times R. Now here we're gonna use the fact that G times GC is much larger than delta G times GC because we're assuming that, in other words, that delta G is small, so it's a small variation in the plant transfer function. So we can rewrite, can simplify the expression as minus GC delta G over 1 plus GGC all squared times R. And well, I don't want to be tedious with the derivations. In the lecture notes, there are a couple more steps, but in the end, I don't really want you to learn all the steps. I want you to understand that in the end, the contribution to the tracking error due to changes in the parameter, and so in changes in the plant transfer function, can be approximated as 1 minus 1 over L of S times dg of S over G times R of S. So dg of S over G is the relative change of the plant transfer function. So once again, here we have that if we want a small increment in tracking error due to the change in the planned transfer function, we want L of S to be as high as possible. And this gives us an opportunity to define the system sensitivity. So the system sensitivity, which is linked to what we've just seen, is the ratio of change in the system transfer function due to the change of a process transfer function for a small incremental change. In other words, the sensitivity is the ratio of the system transfer function, which we're going to just call it TF, over the change of the planned transfer function. So in other words, if the plant changes, how does the overall transfer function of the system change? So here I've used TF as a transfer function, not necessarily T or L, because we can consider actually any system. As a matter of fact, let's take a look at what the sensitivity is for open loop systems. Although we've talked so far about a closed loop system, but in general, we can also define the sensitivity using this expression for open loop systems. So what is the transfer function associated with open loop system? Well, in this case, TF is our loop transfer function, L of S, which is G times GC. So the system sensitivity S is given by delta L over L, so the relative change in the loop, open loop transfer function over the relative change in the planned transfer function. So now we need, we can rewrite this as so d delta L over L times G over delta G, or delta L over delta G times G over L. So delta L over delta G, it's kind of the derivative of L with respect to G. So if L is GC times G, the derivative with respect to G is simply GC. And so we have that dl over dg is GC times G over L, which is once again GC times G. So the sensitivity for an open loop system is 1, is always 1, independently of the actual value of the transfer function GC or G. And is it good or is it not? Well, this is kind of direct. So it means that the system cannot really compensate for variation of the planned transfer function. If you remember in the very first lecture, we said that open loop systems are very delicate because you want to model very precisely your process. If you don't do that, you don't have the chance to modify through using a feedback loop, the performance of your system. So the output is always going to be wrong. So the sensitivity is quite high for open loop systems. And so let's see if the sensitivity can be decreased if we close the loop. So let's take a look at closed loop systems. Well, what is the transfer function associated with the closed loop system? Well, that is our T of S, the closed loop transfer function. So TF is equal to T now, which is GC times G over 1 plus GCG. And so if we calculate the sensitivity function, once again given by now the relative change in the transfer function, that is delta T over T, because of, so over the relative variation of the plant transfer function, that is dG over G, we have that this can be written as G over T times the derivative of T with respect to G. So what is the derivative of T with respect to G? We have to take the derivative of this function. So since it's a fraction, we have the derivative of the numerator. So it's G times the denominator 1 plus GCG minus the numerator times the derivative of the denominator. So GC over the denominator squared. And what is G over T? That is 1 plus GCG times G over GCG. So G cancels out. And so finally, we have that this is given well, first of all, let's realize that this goes away with this. So we're left with 1 over 1 plus GCG, or 1 over 1 plus L of S. So when we are looking at the magnitude of the transfer function, well, we knew that for the open loop system, that is always equal to 1. Here instead, well, it depends on the loop transfer function. So the sensitivity transfer function is 1 over 1 plus L. So if we want the magnitude of S to be small, we need the magnitude of the loop transfer function to be as high as possible. And so this is exactly, this matches what we found here. It's exactly the same analogy, the same analysis. Over here, we studied the contribution to the tracking error due to changes in the plant transfer function. And here we're studying the transfer function associated with the sensitivity, which is pretty much the same thing. Those two things are exactly the same. In control system theory, we usually talk about the sensitivity. So if you're asked to study the sensitivity of a system, that means that you have to take 1 over 1 plus L of S as the transfer function. So let's take a look at an example. So here we're considering a Mars rover vehicle. And so the goal is to operate the rover with low sensitivity to changes in the gain K. So we have the following block diagram for the system. We have a gain K that multiplies the process, which is 1 over S plus 1 times S plus 3. So we want to study how the sensitivity of the system changes as the parameter k changes. So in this case, what we're looking at is the changes in the closed loop transfer function due to changes in the parameter k. So what is the closed loop transfer function, T of S? That is the loop transfer function, so k over s plus 1 times s plus 3 over 1 plus k over s plus 1 times s plus 3. And so that is equal to, if we multiply both numerator and denominator by s plus 1 times s plus 3, we have that is equal to k over s squared plus 4s plus 3 plus k. Okay. So once again here, we can write the sensitivity as k over t times the derivative of t with respect to k. And so now we need to find what the derivative of t with respect to k is. So dt over dk, once again, we have to take the derivative of this fraction. So derivative of the numerator is 1 times the denominator minus the numerator times the derivative of the denominator, which is simply 1 over the denominator squared plus k and minus k cancel out. And so we have k over t is k times s squared plus 4s plus 3 plus k over k times what we just found, so s squared plus 4s plus 3 over s squared plus 4s plus 3 plus k all squared. So the square goes away with this, k and k cancel out. So we are actually left with the transfer function with 2 zeros and 2 poles, but the poles depend on k because k is at the denominator. Anyway, we don't really care here about zeros and poles. We just want to find the magnitude, or to see the magnitude of our sensitivity function. So we can do that by drawing the Bode diagram for the magnitude. So this is the Bode diagram of the sensitivity function. And here I've plotted several curves for different values of k. So you can see that as k increases, the sensitivity decreases for lower frequencies, and however, it has a peak that increases as k increases. So depending on the frequencies at which your system will operate, you might want to choose different values of k. Let's say that the frequency at which you operate are expected to be low frequencies, then you want a high k. But if the frequencies are higher, then the sensitivity of the system has a peak, which is quite high, because here we are 20 logarithm of of the magnitude. For an open loop system, the sensitivity was 1, so logarithm of 1 is 0. So this line would tell you the sensitivity for an open loop system. So we see that the closed loop control system is not always performing better in terms of sensitivity than an open loop system. Because in this case, we have a peak. So all this region here, for this band of frequencies, in which the sensitivity is higher than open loop system. However, for all frequencies lower than that, the feedback control system has a much better performance than the corresponding open loop one. Now we can also plot the Nyquist diagram, since we've seen that, as k varies. So as k increases, I'm going to go towards here, and we can see that the phase margin decreases too. Remember that the phase margin is the angle from, this is the circle with radius equal to 1. So whenever the circle intersects our plots, the angle between the line from the origin to the intersection with the negative real axis is the phase margin. So you see that the phase margin decreases as k increases. So as usual in engineering, we never have everything. We have to compromise on things. If you want a higher k, well, we have to cope with a phase margin that is lowering, and also with a potential very high sensitivity for higher frequencies. However, the sensitivity decreases significantly for low frequencies. Okay, so now I want to teach you how to read, to have a sense for what the sensitivity, or at least for the maximum sensitivity, using Nyquist plots. So once again, the magnitude of the sensitivity function is the magnitude of 1 over 1 plus L of S. So when do we have the maximum of S? Well, that happens when we have the minimum of 1 plus L of S, of the denominator. So what is the minimum of a magnitude? Well, that's 0. So that happens when L of S is equal to, L of S is equal to minus 1. So minus 1 plus 1 would be 0. So in other words, the maximum sensitivity is the closest distance of your Nyquist diagram to the point minus 1. And let's take a look at an example. So here we have a loop transfer function, L of S, given by the following. So we have 0.38 that multiplies S squared plus 0.1 S plus 0.55 over, and then we have S times S plus 1 times S squared plus 0.06 S plus 0.5. And not only are we going to take a look at the sensitivity, but let's also apply the Nyquist criterion. Why not? So in order to apply the Nyquist criterion, we need to know, when we're given L of S, how many poles we have of L of S are in the right-hand side of the complex plane. So the poles of L of S are easy to compute. One is 0, one is -1, and the other two are just the root of the second order polynomial. And so they are minus 0.03 plus or minus I 0.706. So how many poles, sorry, it should be 3 and 4. How many poles of LFS are in the right-hand plane? None, because we don't have positive real parts for them. So capital P is equal to 0. We're going to keep this in mind, but let's first take a look at the Bode plot for L of S. So here we have the magnitude and the phase, and if we want to compute the phase margin for this transfer function, we see that we are quite comfortable, right? Because we have a phase margin of almost 70 degrees. That's great. We're very far away from minus 180. However, there's something suspicious going on. There's this dip here. That means if one of the system parameters changes, we might find ourselves very, very close to minus 180. So in other words, this makes me think that the maximum sensitivity of the system is quite low. From the Bode diagram, this might not be obvious. However, from the Nyquist diagram, things become clearer. So let's take a look at the Nyquist diagram for L of S. So this has this weird shape. Of course, it's this will close at somehow it will close to the right, but we don't really care what happens to the right. We want to see how far away we are from -1. But before doing that, let's take a look at the phase margin. So we have our circle of radius 1 here. It is a little bit squished, so it doesn't really look like a circle. But you have to think about it as a circle. So the intersection of the circle with the Bode plot, here we are. So the angle that this position makes with the negative real axis is our phase margin. And as I said, that this is equal to 69.8 degrees. And it looks pretty cool. We actually also have an infinite gain margin because we never intersect the -180 degrees phase. So the system looks great. However, you see that the minimum distance between the plot and -1, which defines the maximum of the sensitivity, is quite low. So in other words, if the system changed one of its parameter over time, we might go unstable quite fast. So we might change the characteristic in terms of stability of our system quite fast. Before showing you a numerical example of why that happens, let's finish applying the Nyquist criterion. So let's count how many encirclements we have of the point -1. Well, we don't have any because -1 is not encircled. So n is equal to 0. And from earlier, we also had that p is equal to 0. So the Nyquist criterion says that the numbers of right-hand side zeros of L of s plus 1, that is the numbers of right-hand side poles of the closed loop transfer function, is given by z, which is n plus p. Both n and p are 0, so z is also 0. That is, the closed system is stable. Now, if we take the function that we started with, so I'm gonna paste it here. And now we change slightly one of these coefficients. So let's change the 0.06 to 0.04. So you might think, well, nothing's going to change. But remember, the sensitivity, the maximum sensitivity is very high. So even a small change might hinder the whole thing. So before doing that, let's once again compute the poles of L of s. We still have P1 equals 0 and P2 equals -1. And now the other two poles are minus 0.02 plus or minus 0.707 I. So you see that the poles haven't changed much. They used to be minus 0.03, and the imaginary part is pretty much the same. So they haven't changed their location significantly. So still we don't have any pole in the right half plane, so P is equal to 0. But if we plot the Bode diagram, oh boy, we see that all of a sudden our system is not stable anymore, because maybe it's not obvious from the Bode plot, but you can compute the gain margin and you find that that is a negative value, and the phase margin is also negative. And so when both margins are negative, we are dealing with an unstable closed loop system. And let's make sure that that is indeed the case when we analyze the Nyquist diagram, as I taught you last time. So we see now that the Nyquist diagram has also changed quite dramatically. Now we have that -1 is encircled. How many times is -1 encircled? Let's use the criterion that I taught you. So let's draw a line starting from -1, and let's count the intersection with the plot. So we have one intersection here and one intersection here. So at the first intersection, we're going from left to right. So we have +1, and let's see, the direction is this. So at the second intersection, we're also crossing from left to right. So we have another encirclement. So n is equal to 2. So due to the Nyquist criterion, z is equal to n plus p, which is 2 plus 0. And so we have 2 poles with positive real part of the closed loop transfer function. So the system is unstable. If we were to compute the poles of the closed loop transfer function, so just to make sure that we're indeed finding the right result, so we can find that the poles of T, we have two pairs of complex conjugate. The first one is minus 0.52 plus or minus 0.365 I. So that is fine. However, the other couple of complex conjugate poles has a positive real part. So the closed loop system is unstable. So in this last example, we saw that although a system might look or might be stable and might look very far away from being unstable because it has a very high phase margin and an infinite gain margin. But even if that is the case, if the system has a very high sensitivity, very small changes in the transfer function can lead to catastrophic results in terms of stability for the modified system, as happened in this case. All right, so the very last thing that I want to cover is the concept of low, high, and band pass filters and notch filters. And this is going to be quite descriptive and quite fast, but these filters, I'm pretty sure you've heard them. So from the transfer function perspective and from the body diagram perspective, how do they look like? So a low pass filter is a filter, which you can think about it as a transfer function that passes a certain band of frequency and stops another band of frequency. You can determine the cutoff frequency, omega 0, by designing the proper transfer function. So the nominal transfer function for a low pass filter is omega 0 over S plus omega 0, where omega 0, as you know, is the cutoff frequency. So what happens is that if you draw the body plot for the magnitude, it is at 0 decibels before the cutoff frequency. So in other words, the overall gain does not change for frequencies that are lower than omega 0, but um, uh, the gain decreases after the cutoff frequency. So the amplitude of the signal is lowered. So if you have inputs that have frequencies higher than the cutoff frequencies, uh, their contribution is cut off. When it comes to the phase, however, we have the phase goes from 0 to minus 90. And that is because the transfer function associated with a low pass filter is nothing but a transfer function for a real negative pole. So as we know, the phase goes from 0 to minus 90, and at the cutoff frequency, it is exactly equal to minus 45. Now, when we want to do the opposite, when we want to stop the contribution of low frequencies and let pass the contribution of frequencies higher than a cutoff frequency, we use a high pass filter, which is a a zero at the origin combined with the real pole. And the cutoff frequency is always omega 0. So we're coming from minus infinity with the slope of plus 20 decibels per decade. And then we flatten out at 0 decibels after the cutoff frequency. Here, the phase goes from minus 90 to 0. You can combine a low pass and a high pass filter to create a band pass filter. So in this case, you're gonna let only signals with frequencies in a certain band that goes from omega L to omega H, so low to high. And this band of frequencies is centered around your cutoff frequency, omega 0. Here, in terms of phase, the phase goes from plus 90 to minus 90, and it is 0, corresponding to the cutoff frequency, omega 0. Finally, we have the notch filter, which is instead a band stop filter. In the band pass filter, we would pass only signals with frequencies in a determined band. And here we're doing the opposite. We're blocking a band of frequencies. So the transfer function associated with the notch filter, I've written it over here. So we have a couple of imaginary zeros, and then two complex conjugate poles. We have three parameters in the transfer function. We have omega z, which is known as the zero circular frequency. Omega p is the pole circular frequency. And finally, q is known as the q factor. So if we have a low q, then we are going to stop a wider bandwidth of frequencies. And instead, if we increase q, then we stop a narrower band of frequencies. And if q is high enough, the band is so small that we're effectively removing maybe one frequency. If we don't want your system to be affected by a specific frequency that might happen in your input, then you can apply a notch filter to knock down the effect of such frequencies. And we're going to see it in a minute. You have three types of notch filters depending on the relationship between the zero circular frequency and the pole circular frequency. If the two are the same, that we're talking about a standard notch filter. If the zero circular frequency is higher than the pole circular frequency, then we have a low pass notch, and vice versa, we have a high pass notch. Now, if we're taking a look at the standard notch, so omega p is equal to omega z, and we're gonna name it omega 0, and we're gonna let q vary. So the transfer function reduces to s squared plus omega 0 squared over s squared plus omega c times s plus omega 0 squared. And in this case, when the two circular frequencies are the same and equal to omega 0, that is called the central rejected frequency. That is the frequency that you're rejecting. But you cannot really reject only one frequency. That is the peak of your rejection. However, you're going to reject a band of frequencies, and the width of the band is omega c, which is given by omega 0 over q. So the higher q is, the narrower the width of rejected band frequencies is. And we can see here the Bode plot for a notch filter. So you can see if we increase q, where the magnitude goes lower and lower, so we are rejecting more effectively a narrower band of frequencies. So if q tends to infinity, then we're the negative peak would go to minus infinity, and it would be centered exactly at omega 0. And in terms of phase, well, we have that the phase starts at 0, it lowers to minus 90, and then it starts right after the rejected frequency at plus 90, for then lowering its value back to 0. If q increases, and if q is pretty high, then the phase it's at 0, and then it suddenly jumps from -90 to +90 and then goes back to 0. So if Q were infinity, we would have a discontinuity. Well, we'll still have a discontinuity in the phase, but that would be just pointwise. Okay, so this concludes the course. So I'm gonna see you later for the Q&A session. So come prepared with your questions. And it has been a pleasure being your instructor, although with the weird circumstances, once again, due to the pandemic. Hopefully we can come back to school and have normal lectures and normal interactions. However, good luck to everyone and take care. Bye-bye.